So a small video on the mean value theorem, which is 4.2 of that Thomas book, and it talks about if f of x is continuous on a closed interval from a to b and differentiable on the open interval from a to b, then there exists a c somewhere between a and b such that this happens. So f of b minus f of a all over b minus a is equal to f prime of c. Now graphically, what it means is if I have a green function, y equals f of x, and I can see that it's smooth and continuous. So it's continuous and then also differentiable. The red is the secant line, which really is like your average rate of change from a to b of your green function f of x, and the blue line is the tangent line at c. So what the mean value theorem says that if this green line is continuous, I can draw it without lifting my marker from this closed point to this closed point, then the slope of the secant line, then somewhere in between a and b, the slope of this green line, the tangent line, is equal to the average rate of change. So slope of the tangent line, the secant line being this piece, and the slope of the tangent line being this piece. So we can really, prove this or verify it for a couple examples. So let's try one quick example. So given, say, f of x is equal to the natural log of x on, say, 1 to 3. Let's show that this works. So really what I have to do is I have to verify that this function is continuous and also differentiable on this continuous on the closed and differentiable on the open. And what we can see is this function is defined everywhere, on this particular interval. If I would say maybe from 0 to 3, we'd have a problem because this has a vertical asymptote at 0. But it is, it is continuous from, 1 to 3. So that means somewhere between 1 and 3, the slope of this, or the slope of the tangent line of this is going to be equal to its average rate of change from 1 to 3. So, the average rate of change being, f of b, so f of 3, so log of 3 minus f of a, so log of 1 all over 3 minus 1 is going to be equal to the derivative of this thing at some value of c. So what I'm going to say is I'm going to call it f of x, or f prime of x. I know you should probably say f prime of c, but I'm going to say f prime of x, and when I solve for x, that'll be my c value. So, the derivative of this function is going to be 1 over x. If you want like f prime of c, you can say 1 over c and then solve for c if you want to as well. But I'm going to see it as, leave it as 1 over x. So now I'm just going to solve this for x, and I'm going to verify that that x value is contained, in this closed interval from 1 to 3. So, actually, this is not too bad. Natural log of 1 is 0, so that goes away. So this is going to be the natural log of 3 over the natural log of 2. Natural log of 3 over, 2 is going to be equal to 1 over x. So, multiplying x is going to be equal to 2 over the natural log of 3. So if I calculate that, two divided by natural log of 3, I get 1.82, about 1.82. Well, really, I'm just verifying that it does live between this interval from 1 to 3. Now, another set of problems. So this is kind of very similar to the very first set of problems. Another set of problems says identify if the hypotenuse of the mean value theorem is satisfied. So let's do a couple examples of that. One where it's satisfied, one where it's not. So I'll leave it up. I'll just write it down here for a second, then eventually we will really erase it and just note it. That. So let's say verify the mean value theorem is satisfied. And then in another one, we'll show that it's not satisfied. So say for this one, we have f of x is equal to the square root of x times 1 minus x. Since from 0 to 1, I'm actually kind of curious if this is not satisfied. Do 1 plus x. How would that work? And this is going to be on, say, 0. Well, what I want to do is I want to verify that, actually, I'm going to leave it as 1 minus x. I have a feeling that it works for this one, but we'll know in a minute here. So I want to verify that this is really it's continuous on the closed interval is the biggest thing. Then we can also verify that it's differentiable, but if the function tends to be continuous in the closed, it tends to be differentiable on the open, but that's not always true. So let's find the domain. So the domain of this function is going to be, when this happens when, let's do colon here. This happens when the radicand is greater than or equal to 0, because this is a rational. So, sorry, a radical. So what we have is going to be careful because this is quadratic in nature. So, we have x minus x squared is greater than or equal to 0. So a good way to look at that is to look at the graph of this thing. And we do know that this is a parabola that opens down because I have a negative x squared. This is minus x squared plus x is greater than or equal to 0. So I know that it's a parabola that opens down, but I also know it's zeros. The zeros are going to be 0 and also 1. So what you'll see for this, remember, I'm graphing this quadratic, not the original function. I want to find when this thing is greater than or equal to 0. So it's 0 at 0. It's also 0 at 1, and the thing opens down. So what we can see is that it is greater than or equal to 0 from 0 to 1. So the domain of this thing is just, 0 to 1. That's its domain. So what that means is, since this function is domain lives from close 0 to close 1, this thing is going to be continuous from close 0 to close 1. And then I guess if we want to take its derivative and verify that that thing is also differentiable from there to there, we might as well do that. So actually, you know what? This would be a good practice for doing logarithm differentiation. I think that might be helpful. So if I wanted to do this, what we can do is we can natural log both sides. So natural log that left-hand side and I'll natural log this right-hand side. And you guys asked for more of these examples. Otherwise, I'm going to have to use a chain rule. So, this is 1/2 power. You have to bring that out front, drop it by 1/2. And then when you take the derivative of the inside, you're going to have a product rule. So it's a little bit messy. So maybe logarithm differentiation will be a little bit easier. So this is nothing more than the 1/2 power that we just discussed. So with logarithms, you can pull the half out. So natural log of this product of 1 minus this. Now the log of the product is the sum of the logs. So this is going to be 1/2 times the multiplication of what I get here. So the multiplication of 1/2 times the addition of these logarithms. And then you can distribute the 1/2 through. And now we can take the derivative. So this is nothing more than just logarithmic expansion. Now the derivative of this is much easier than what we had before. So the derivative of y is going to be 1 over y times the derivative of y, because this is implicit form. So dy dx. And the derivative of this, since it's just sums, is pretty simple. The derivative of this is 1 over x times its constant. So 1/2 times 1 over x, or 1 over 2x. Derivative of this is going to be 1 over 1 minus x times the derivative of the inside. Derivative of the inside is going to give us -1. So this is going to be minus, 1/2 times, 1 minus x. Now I multiply by y. So dy dx is going to be, send the y to the other side. Remember, y is this thing. So this is going to be y times, this. And remember, this thing is differentiable when its derivative is defined, and its derivative is defined, well, so far for this piece, it's, closed 0 to closed 1. But you can see that over here, it's open 0, open 1, because if I plug in 0, this thing's undefined. If I plug in 1, this thing's undefined. But that's fine, because remember, it just has to be differentiable on the open interval, so the endpoints are don't really matter. So far, this is, continuous here, and it's differentiable here, so we are good to go. So that means that this will actually work. So I don't really want to solve this for x. They're not asking for that. So what we could do is this would work. I could plug 1 into here, 0 into here, and then 1 minus 0. At least the denominator will be equal to 1. And I could evaluate the functions pretty easily. So I could find this pretty easily, and then I have to set it equal to this piece. But solving this for x is I'm not going to do it. It'll take way too long. So they're not asking for that. They're just asking us to verify the theorem. So I do know that somewhere between 0 and 1, that the slope of the tangent line of the slope of the tangent line is going to be equal to the average rate of change. Now let's do one where it fails. So let's do a piecewise function, because I know it's going to fail here. We have say this is number 11 in this particular book. So show mean value theorem is not satisfied. At least the conditions, I mean, these two conditions are not satisfied. So we have f of x is equal to x squared minus x. This goes from -2 less than or equal to x less than or equal to -1. And then 2x squared minus 3x minus 3. And this is from -1 less than x. Ava, I'm recording. Please give me a little bit. To 0. Okay, so I think it is continuous on the close, but I doubt it's differentiable. So what I know is that, it's this quadratic from -2 to 1, and it's this quadratic from -1, sorry, -2 to -1, and this quadratic from -1 to 0. So I have a feeling it's going to look something like, it's going to be some quadratic from, -2 to -1, and then it might be some other quadratic, and I'm not sure its slope, but let's just make it look funny. So let's say, I know it doesn't look like this, but let's say it looks like this, for instance. And this is going to be from -1 to 0. I know it doesn't look like that because that'd be a quadratic opening down, and this has a 2. So, but this gives a better picture. We can see that it's continuous from -2 to 0, but it's not differentiable here because it's sharp. It's a sharp point there. So really, like, the slope from this direction doesn't match the slope from this direction. So, it wouldn't have a tangent line at this particular spot. It kind of wobble, I guess would be the best way to describe that. So first, let's start out with continuous. Now, I know this function here is continuous from -2 to -1, and this function is continuous from -1 to 0 because they're both polynomials, not undefined anywhere. So I just have to verify that they connect at that particular point. So let's plug -1 into here. Let's plug -1 here and see if we get the exact same y value. So let's just test continuous. The only problem is that this -1 again, smooth and continuous here, smooth and continuous here, but when it jumps from one function to the other, maybe not. So -1 squared minus -1, and this is going to be equal to 1 plus 1. So this is 2. And my question really is it equal to this thing at -1? So 2 times -1 squared minus 3 times -1 minus 3. So this is equal to 2 plus 3 minus 3. This is 2 as well. Okay, so far I can prove that it's continuous. Again, the only suspect point was this -1 where it changes from one function. So continuous, well, okay. From A to B, from -2 to 0. Now, differentiable, that might be a different thing. So let's find the derivative at for this one. So for -2 to -1, f prime of x would be equal to 2x minus 1. And on the interval from -1 to 0, f prime of x is going to be equal to 4x minus 3. Now, we do know that this function is, it's differentiable on this entire interval. It's still a polynomial. This function is differentiable on this entire interval. It's still a polynomial. The same suspect point happens to be at that -1. So let's plug -1 into here and plug -1 in here and see if we get the same slope from both directions. So I really want to see if something like, if something like that happens. Oh, that's bad looking. But I want to see if there's some kind. I'll draw it the ugly way, but I want to see if we get some kind of sharp point here. I want to see does the slope from this direction equal the slope from this direction. So plugging in, f prime of -1, which is 2 times -1 minus 1, so this is -3. Over here, f prime of -1 is going to be 4 times -1 minus 3, so -7. So the slopes don't match. It's going to be sharp there. So so it is not sort of testing differentiable on the entire interval. So from a to b, -2 to 0. So from -2 to 0, it's differentiable here. It's differentiable here, but it's not differentiable at that -1. So this is not differentiable on the entire interval. So that means this is not going to be satisfied. Well, it still possibly can be satisfied. I just can't guarantee it. There still might be a point there, but we cannot guarantee that there is one. All right, so yeah, let's move on to one more example. There's a couple different ways. So the last main type of problem sets in here are asking to prove that there is exactly 1, 0 between this, and it's really just this tends to be properties of continuous functions. So let's say do it in class. I'll do it again. So what it wants us to do is show there is exactly 1, 0 in the given interval. So f of x, say f of x is equal to x to the fourth plus 3x minus 1, and this is going to be on -2 to -1. All right, let me show you the approach. So what I want to know is we have, from -2 to -1, I have a function here. And what I really want to do is I want to see, I know this function is a continuous function, it's defined everywhere. There's no denominators, there's no radicals, no logarithms. So it's defined everywhere. There's no asymptotes is what I mean. So if I can show that it is positive or negative up here, and then it is negative or positive down here, that it changes sign from one side of the interval to the other. Since it's a continuous function, it's got to cross the x-axis. That means there has to at least be 1, 0 there. Now, just a little bit. So there's got to be at least 1, 0 there. So if it's positive up here and negative down here, it's got to cross that axis somewhere. So, but that's not the only thing. That just shows that there exists, at least 1, 0 doesn't say so that shows 1, 0, but it could possibly do stuff like this, right? It could possibly do something like that. I'm unsure if it bounces more than one or so, if it changes directions multiple times. So what I want to show is I want to show that it's that they change signs from one side to the other. So if it's positive up here, then it's got to be negative down here. If it's negative down here, it's got to be positive up here. I have to show that it at least crosses once, and then I want to show that it crosses only once after that. So let's start with explaining how we verify that there's only one. So what I'm going to do is I'm going to make sure that there are no critical points inside this interval. Critical points mean the derivative is equal to 0. So if this happens, I have a critical point here, and I also have a critical point here. So there's at least one critical point, and which means its derivative is equal to 0 at those particular spots. So I just want to verify there are no critical points in that, because if there are no critical points in there, what you're going to have is this is the only way. So if it goes from here to here and there's no critical points, that means it doesn't change direction. That means it's only gonna cross it once. So I want to make sure that doesn't happen. I want to show that this happens. Okay, so first let's figure out the values. So let's figure out what is f of -2 equal to, what is f of -1 equal to. I just want to show that they're different signs. I just need to show that they cross the x-axis. That's the only way to change signs, is to cross 0. So y equals, we have x up to the 4th plus 3x minus 1 enter. And let's go -2 and -1. Okay, so at -2 we got 9, and at -1 we have -3. Okay. So this is 9, this is -3. So I can see that it did change signs, so it does have to cross an x-axis, at least once. Now I just have to verify it crosses only once. So let's find critical values and make sure that there are no critical values on this interval. So a critical point. So critical points, and this happens when f prime of x is equal to 0. So the derivative of this thing is 4x cubed plus 3 is equal to 0. So solving for x cubed, so subtracting 3 divided by 4, and then cube rooting. So this is going to be the cube root of -3/4. Boy, I hope it's not between -1 and 2, because we'd have a problem. So -3 divided by 4 up to the 1/3 power. I get about -0.91. So this is about -0.91. -0.91. So it happens actually right here. So there are no critical points inside the interval from -1 to 2, which is now we verified. There is verified. There is only 1, 0. Now, the way I found its values is I plugged it, into the y equals. See if you can see that. I plugged it in the y equals. And then if you go to not your window, but your table set, if you hit second table set, and you make sure that the first one says ask and the second one says auto, so you want your independent, which is your actuality, to be ask. Instead of hitting graph, you go second table sets, and now you can plug in the numbers that you want. You can plug in the numbers that you want. Now I know there's no critical points between there. So if I was a computer and I want to isolate this to 0, what I could do is I can pick closer numbers. Let's go like -1.6, and let's go say -1.2. Well, actually, you can see I've tightened the interval a little bit, and I still have a negative output and a positive output. So positive output first, negative output second. So that means that there's 1 0 between those two numbers. So you can get a little bit better. Let's try like -1.5 to -1.4. Well, that didn't work because they're both negative. So let's try this. So -1.3. 0.4 answer, -1.2. Let's try that. Still didn't work. There you go. I got two new ones. So -1.6 and -1.5. I can see that one output is positive, one output is negative. So it lives between there. And you can kind of continue with that process to be able to narrow down that 0 if you choose. That's really the gist of this. So hope that helps.